So we know now that there's 4 statements that we built here, 4 compound statements, each of which we agree to be true. The first one, 6 is not a prime number. The second, the moon is not made of cheese. Third, dolphins are mammals, or 6 is a prime number. That was true because one of its component pieces, namely dolphins are mammals, was true. And as soon as one piece is true, the whole disjunction is true. And then the fourth statement was, if the moon is made of cheese, then dolphins are mammals. That was true vacuously because its premise was false. Right? So next the question is, how can we negate statements? How do we form the opposite of a logical statement? So how do we make a false statement out of the negation of these 2 true statements? So let's go one step at a time. First, thinking of the conjunction, Q or R. Dolphins are mammals, or the moon is made of cheese. What would it take to negate that statement? What would prove that Q or R is false? Remember, the disjunction, the or statement. The or statement is true whenever even one of its pieces is true. So in order for it to be false, we need for all of its pieces to be false. So the negation of P or Q is the conjunction, the and, of not P and not Q. So the or statement fails only when all of its individual pieces are false. That's the first of what we call De Morgan's laws for logical propositions. The only way you can prove that P or Q fails is if all of its pieces fail. So we see the disjunction turning into a conjunction when we negate it. That's not the last time we're going to see a phenomenon like that today. So if I wanted to make a negation out of Q or R, so I'll put a not symbol in front here and write something like, it's not true that dolphins are mammals or the moon is cheese. What would be another way to write that, according to De Morgan's laws? If I wanted to prove this statement to be the case, I need to show 2 things. Both hold. I need to show that it's not true that dolphins are mammals, and I also need to show that it's not true that the moon is cheese. And so we would write not Q and not R. Dolphins are not mammals, and the moon is cheese. So one of the things you notice when you start to actually do mathematical work with compound statements, right, is that proving an or statement to be true is pretty easy. We just have to find any one of those pieces which is true. And if we show that that one piece is true, then the whole thing becomes true. But if I want to falsify an or statement, it's a lot harder, right, because it becomes a conjunction instead of a disjunction. To prove the statement is false, an or statement is false, I have to show that all of the negations are true. Every one of the, all the negations are false, right? That none of the pieces present in the original conjunction are in fact true. So however simple it is to prove a statement, usually proving the opposite of that statement is easy where the original was difficult, or difficult where the original was easy, right? So that's not too surprising when you think about what negations are doing. If proving a positive is easy, proving a negative is hard, and vice versa. So similarly with the conjunction, P and Q was true only when both of P and Q were true. So if I wanted to show that P and Q is false, I just need to find a single chink in the armor. I need to find one of the pieces that make up my conjunction and show that that one piece is false. So P and Q is false exactly when either P is false or Q is false. That's the second of the De Morgan's laws for logic. Each of these De Morgan's laws for logical propositions has a corresponding De Morgan's law for set, unions, intersections, and complements. And you'll see those in our next session, session 2 on set theory. And so it's the implications, the if-thens. These are the ones that are the most interesting with what happens with an implication statement when we try to negate it. One of the reasons, or one of the ways we can prove what happens here is that we can rewrite an implication. Remember, an implication is true when either its premise is false. So if the premise is false, it makes the whole implication true. So if not P is true, then that makes P implies Q true. And the only other way for an implication to be true is if both the premise and the conclusion are true. So there is a way of writing a implication P implies Q in terms of ands, ors, and nots, the basic elements of set algebra. And so what that does is it actually lets me find the negation of an implication, so not P implies Q. Right? I can do that just by taking not of this whole thing and applying my De Morgan relations. Right? The not, when it distributes into this or that's in the middle, actually gives me an and. Right? And when it distributes into this not P, I get not P, which gives me P. And then when it distributes into P and Q, I'll get not parentheses P and Q. But according to De Morgan, not P and Q is not P or not Q. And so I can rewrite this as P and not P or not Q. But one of the fundamental truths in logic, the law of the excluded middle, says it's not possible for P and not P both to be true, right? Because every proposition has to be either true or false. There's no middle ground and there's no none of the above. And so it's never possible for this disjunction to be true because not P is true, and then not P ands with P here. That's always going to give me something false. So when I simplify this out, that not P can actually be canceled. And we get a negation that looks like P and not Q. So when I negate an if-then statement, the only way to prove that an if-then statement is false is to find an example where the premise holds, but the conclusion fails. So when I negate an if-then statement, what I end up getting is premise true, conclusion false. Hang on to that because that forms the basis of how we structure a proof by contradiction later on. In a proof by contradiction, we try to show that P implies Q is true by showing that it's ridiculous that P implies Q would be false. So we assume P implies Q is false and then try to show that something else ridiculous happens. Something that we know to be false ends up happening later on down the line. And so if I want to negate the statement, if the moon is cheese, then dolphins are mammals, so that we decided was a vacuously true statement. To form the negation of that, the negation, notice, is no longer an if-then statement. My little right arrow is no longer present over here. And so the negation is a conjunction. If it's not true that R implies Q, then that means that the premise would have to be true and the conclusion would have to be false. And writing that out in words, this would say something like, the moon is cheese and dolphins are not mammals. Which again, we can decide for ourselves that that is in fact a false statement because dolphins are in fact mammals. So this clause ends up being false, and that makes the entire conjunction false, which makes sense because our original implication was true. So figuring out how to turn an implication or a logical statement on its head to negate it is a really important skill for analysis, one that's underrated and one that we'll get a little bit more practice working with as we go forward into these last couple of topics today.